Hello, my name is Changju Lee from Sensor-Technik Biderman. Today, I want to give you a presentation on evaluation of perception sensor for safety of highly automated machine operation. Safety is one of the primary concerns of highly automated machine operation, and many manufacturers have introduced some environmental perception system to reduce safety-related risk in automated machine operation. Especially safety and reliability are fundamental requirements for the design of the perception system. So understanding the sensor characteristic and choosing the right sensor is a critical part of starting the system design. So main goal of this presentation is to show a systematic procedure for the comparison of different perception sensors and evaluating their stability in the context of a given use case. So these slides show a basic principle of perception system. Perception system comprise perception sensor to gather information about the machine surrounding. These perception sensor pass the information to algorithm for detecting, localizing, and classifying a potential feature of interest. So the main purpose of this perception system is to provide information for safeguarding system and safe control of the machine. However, there are major challenges in realizing a safe and reliable perception because there is no sensor that works perfectly to cover the desired detection boundary in all situations. Unfortunately, the perception sensor always have a risk of failing falsely or late detecting obstacle. These three show different type of risk parameter affecting the detection reliability of perception system. So firstly, the environmental parameter include the variety of environmental stress such as sun radiation, darkness, and all kinds of atmospheric precipitation and condition. And second, the obstacle-related parameter include object property to be detected, such as high or poor reflection property, object dimension, object moving speed, and surface condition. Third, machine-related parameters include hardware and software issues such as high vibration from engine or demand for the processing power and misalignment of a sensor and high operating speed or dirt on the lens. This risk parameter can cause malfunction and lower the confidence level of perception sensor. Therefore, it is essential to take into account operational and external factors for the system development. So, considering both technical requirement and detection reliability is crucial part for the design of functionally safe and reliable system. For the evaluation, we define two terms: technical performance and detection reliability. This technical performance contains measurable key criteria that satisfy system requirements or technical goals such as perception range and frame rate or range accuracy, repeatability, and so on. Normally, this value can be obtained from the technical specification. And second term, detection reliability is an index of performance that describes how consistently sensors detect the required information in varying situations, such as environmental and obstacle-related and machine-related parameters are the criteria that affect detection detection reliability of perception sensor. In this slide, I would like to introduce an autonomous mobile machine with obstacle detection function as an exemplary use case to illustrate the evaluation procedure in this presentation. So the maximum operating speed of machine is 33 km per hour, and the machine operates in bright, low light, and dark condition, and the perception system must detect the positive obstacle in moderate and low rain condition. So for the evaluation perception sensor, we chose different criteria in terms of technical performance and detection reliability. For the evaluation technical performance, we select 5 criteria: precision range, refresh rate, pixel and point density, range accuracy, and repeatability. Especially, we define a new criteria: tarion, pixel, and point density to compare the resolution of sensor with different field of view easily. And so the criterion normalize the sensor resolution to 1 degree of vertical and horizontal field of view. So next, for the evaluation of detection reliability, we selected 2 parameters: environmental parameter and obstacle parameter for the evaluation. So comparing technical performance with technical datasheet is quite clear and easy step. However, when it comes to the evaluation of sensor detection reliability, we need additional knowledge of sensor behavior. So we have conducted a larger scale field experiment with this test platform. And the test platform consists of 4 parts: perception sensor and control unit used for the data collection, and portable battery, and laptop PC for real-time sensor monitoring and data logging. And we chose 7 different perception sensors, and each sensor has different sensor modality and is operating different electromagnetic wavelengths. And as you can see, sensors were mounted on the adjustable profile. And additionally, the weather sensor was used to measure air temperature and relative humidity and illumination. And inclometer and gyro sensor were used for the ground temperature information. And the control unit provide external interface for perception sensor and use ROS middleware to integrate them into a common framework. For the field test, we chose 5 different test obstacles by considering obstacle parameter and our use cases: isolator person and 2-waste container and loss sign. Each object had different appearance, material property, and surface condition. Especially the isolator is defined in ISO standard and represent a seated human. It has a olive color and was filled with water. And person and 2 container and the high reflective road sign were relevant to our use cases. And for the measurement of the test objects, the test platform was installed at 8 meters away from the obstacle. So for the practical test, we chose 3 different ground conditions and also 3 different solar intensity. In addition, as a foreseeable obscurity, we chose moderate rate condition and target area to see how obscuration of the obstacle affect the detection confidence. Here you can see 3 different images captured by RGB camera and near-infrared camera and thermal camera. This imaging sensor detects the natural radiation that is emitted or reflected by obstacle or scene. In bright light condition, all objects could be easily distinguishable from the background, but one difference is the thermal camera could not recognize the arrow symbol on the road sign because the surface of temperature were uniform. In dark condition, only thermal camera was able to see the object clearly. Compared to the RGB camera, near-infrared camera show a better night performance, but has a poor contrast image compared to thermal imaging. And right side of image show the interference between near-infrared camera and 3D LiDAR. As you can see, 16 layers of LiDAR beam were observed in the near-infrared image because the near-infrared camera could measure the wavelength region of the LiDAR beam. And the below 3 images show the result of the capture in front of tall grass where the person is hiding behind the grass. In the RGB and near-infrared image, the person could not be distinguishable. However, the thermal camera achieved high degree of bush penetration compared to both cameras. This slide shows the result captured by stereo camera. Stereo camera reproduces the way human binocular vision works using stereo matching algorithm and therefore provide for field of view 3D measurement. As you can see, in bright light condition, the stereo camera could measure some object and the grass with high point density. However, in a parking lot where we test, some part of waste container and the ground tile were not measured because the homogeneous region and repetitive pattern made sensor difficult to match the stereo pair properly. And the light image showed the result of 3D measurement from stereo camera in low light condition. As you can see, the stereo camera failed to measure the object because the stereo camera matching algorithm could not find collecting feature point in pairing image. And this image shows the test result conducted on the moderate light condition. The results show that the stereo camera could measure the morphological characteristics of objects in moderate light condition. However, some parts of ground were not detected because of homogeneous region cause stereo matching ambiguity. In this slide show the result captured by time of flight camera. This time of flight camera measures distance by actively illuminating an object with a modulated light source. So normally this type of sensor is very compact and provides short range. And as you can see, the result measured in bright light condition show that all objects were hard to distinguish from the background because of the potential noise from bright sunlight. And next scenario, measured in parking lot, shows many reliability issues as well. As you can see, the isobator and left part of green waste container could not detect it because a sufficient amount of emitting light could not reflect in the direction of the sensor due to the surface foam. And the person's black trouser and black waste container could not be measured because black objects observe a lot of light and less light reach the sensor. And the road sign and the highly reflective bed stripe were not measured as well because highly reflective objects reflect too much light source and cause the sensor's pixel to saturate. And also non-existent point around the road sign were measured. The main reason is the reflective light was scattered between the pixel and the lens attached to the sensor. The scattered light reached the several pixels and corrupt these pixels. This was measured. In moderate rain condition, it could not measure anything because enough active light source could not reach to the sensor due to the rain. This slide shows the result measured by 3D lidar and FMCW lidar. LiDAR and FMCW radar detect range by targeting an object with a laser and radio wave and measuring the time for the reflected light to return to the receiver. So as you can see, the upper image shows the result of point cloud measured by LiDAR and FMCW radar in moderate light condition. And the results show that the radar and radar were able to consistently detect the ice pattern in both rain conditions. However, in the case of a lidar, much of asphalt ground was not detected because the water on the asphalt ground observed laser signal. So the laser signal is observed by the water. So below image shows the result measured in front of tall grass where person were hiding behind grass. So in this case, the both lidar and radar could not measure the person through the dense bush. So to design safe and reliable system, the potential risk issue must be identified by testing, simulation, and use of statistical analysis to minimize the known and unknown potential danger scenario until the remaining residual hazards are acceptable. And then the perception sensor or system must be verified to ensure stability and completeness for its intended use. So this slide shows evaluation result for the comparison of different sensors and evaluating their suitability in the context of the given use case. So the perception sensors are evaluated in terms of technical performance and detection reliability, and each perception is rated according to its evaluation criterion on a 6 rating scale from 0 to 1, and the higher the rating value means the higher the stability. And the system requirement is equivalent to a value of 0.8. And so now value exceeding 0.8 means the over performance of the sensor. So next step is numerical comparison. This step is shown in table below using the example of the stereo camera for the defined use case. And each criterion is weighted with the value between 0 to 1, and which represent the importance of the criterion. And then also the criterion is rated on a 6-point scale, 0 to 1, and now a normalized evaluation value for each sensor can be calculated by sum of weight multiplying rating value divided by sum of weight multiplying maximum rating value. And finally, the normalized evaluation value can be calculated in terms of technical performance and detection reliability. So the main advantage of this numerical comparison is that it can easily specify requirement for the performance of individual perception sensor and also quantify that performance through the data. And it provides basic guidelines for selecting perception sensor to meet system requirements. Designing functionally safe and reliable perception system is a challenging task. Choosing the right sensor or sensor combination must be carried out systematically because sensors perform differently with respect to various criteria depending on their sensing technology. The presented evaluation procedure is a helpful guideline for system engineers to carefully select sensor when designing safe and reliable perception system. By conducting a large-scale sensor field study, Sensor-Technik Wiedemann has gained profound technical know-how and experience in sensor performance in practical operation and in designing suitable sensor configuration for application in highly automated mobile machine. This qualifies Sensor-Technik Wiedemann to provide customers with the appropriate hardware, software toolchain, and consulting service, thus enabling high-quality solutions for the automation of mobile machine. Thank you for your attention.